much for the introduction, and would like to thank the organizers for the invitation. As you see, the talk is on development of modules for applications in this area here, and I will mainly talk about one idea we have to improve the power output, and also how to consider the reliability issues, which are a major challenge here. So I will just on one slide show what Fraunhofer Center Silicon Photovoltaics is doing. Then I will give you a motivation for the investigation. I will briefly talk about technologies, especially crystalline technology, and then I will focus on some technical challenges, how to increase the energy yield from photovoltaic systems, crystalline-based silicon, and the second topic will be how to deal with some reliability issues, and I will talk about two things: is potential-induced degradation, which is a very important thing, the influence of temperature changes between day and night on the influence of the fatigue of the interconnections, and I will give you a short outlook of some current activities which we have in dust and soiling investigations. So Fraunhofer Center Silicon Photovoltaics was founded in 2007. We are currently roughly 120 people. There are 70 researchers. We have two locations in Germany, one main research center, and this one here is a module line where we have full capacity to produce even large modules, which you see for different installations. I will come back to that later. We work along the entire technology in photovoltaics, crystalline photovoltaics again, so from crystallization of silicon under characterization, module technology, and module reliability. And today I will talk mainly about the module reliability and technology issues. So motivation, first of all, a few words about our cooperations which we have. I mean, if we are talking about modules for desert applications from Europe, you can design and you can think about a lot of ideas you have, but in the end of the day, you need some cooperation partners which can test modules under the specific climate conditions. And as Professor NOE mentioned, we have a cooperation for several years together with the IRSEC' here in Morocco, and we helped to design that test platform here in Ben Guilhem. And this is right now the largest PV test platform in Africa. There are more than 10 technologies which are currently tested in parallel from different companies, thin film, but also crystalline technology. And since a while, we also have a cooperation with the Kerry in Qatar in the analysis and improvement of modules under desert conditions in Doha. So motivation, why to develop some modules which are really dedicated for desert applications. One is that the amount of installations in that area here, northern part of Africa, Arabic Peninsula, will increase over the next years. There are different predictions. The battery is running low, so it's not my computer. So if somebody has some power, right, there is a power here. So. Oh. We have a cable? I think I got the power back, yeah, and also the connection. Okay, great. What are the challenges? Obviously, there's a big challenge for, it's fine, yeah, so big challenge for market entrants because of the political situations and also regulations which differ from country to country. But the topic I'm going to talk today is the environmental conditions, which are completely different to the installations or the experiences which we have in Europe and in America. So we have higher temperature as mentioned, we have soiling, we have abrasion, or we have dust issues. And as mentioned in the talks before, in order to make a photovoltaic competitive, the levelized cost of electric energy, levelized LCOE cost, they have to be competitive with fossil. So this is the goal which we have to reach. And if you do such an analysis, there are a couple of factors which will influence the cost situation. It's obviously your investments and interest rate. But from a technical point of view, it is very important what is the produced electric energy, and this is related to the efficiency of the solar cells, the modules, performance, and also the irradiation, so that means the local conditions. And on the other hand, it is very important how long your system will work. So that's the years N here, and you have to make sure that this degradation rate is as low as possible. So therefore, I will focus on those two topics. So how to increase efficiency for the specific applications and how to consider the specific requirements on lifetime and availability in this application. So if we follow the calculations and predictions of levelized cost of energy, so this is from the international roadmap of the PV industry. What you see here are the prediction how the levelized cost of electric energy will develop in the next years, and that's for different irradiation conditions. So the blue one is something like Germany, and Morocco we are between the 1,500 and the 2,000. And you see the predictions are that in very sunny regions in the world, in 8 years, the cost to produce a kilowatt hour of electric energy will be something like $3. If you compare that with some recent analysis, in this case from the energy agency in the United States, so they say if you buy or if you build a new power plant which is based on fossils or on nuclear, you are in that range of energy production, which obviously strongly depends on the cost of fossil, which can differ from time to time on the market. And the main information from that slide is if a system can work for 20 or 25 years with the current costs which we have in PV, this energy will be really competitive to fossil technologies, and we can produce energy for lower costs in the next years. And just one example, and as I just talked with somebody from Aqua Power, so this is also one system which I think it's 200 megawatts I just learned, but this is something which you see follow this line. So the production of around $6 in Dubai, in an area with a very high radiation. So that means it's not only a prediction, this is also something which becomes true in the next years. So which technology you choose for a photovoltaic system? There are a lot of technologies around, and there was a lot of investigation. Still there are a lot of technology developments, but it turned out this crystalline technology is really the dominating technology in the market right now. So there are different materials used, monocrystalline silicon or multicrystalline silicon, but you see in 2006 there was the prediction that thin film silicon will have in 2015 something like 20 or 25% of the market share, but right now we see a reverse trend. So the crystalline silicon is increasing, and this year we will have more than 90% of all modules produced worldwide and installed worldwide from crystalline technology, crystalline silicon technology, and there are a lot of good reasons that this will not change in the next 10 years. It is the dominating technologies, just the pure volume which the big manufacturers have. It is established, there is experience of more than 30 years, and the big companies, they will have production capacities of 5 gigawatt next year. And if you start with a new technology, it is extremely difficult to compete with that cost structure. Thin films, as mentioned, they are smaller than 10%, and as mentioned, the trend is even that this share will increase in the market. It's mainly cadmium telluride and CIGS. Thin film silicon nearly disappeared completely in the market. There are advantages, definitely, lower temperature coefficient, Nevertheless, the efficiency on the module level is below the crystalline silicon, and so far none of those technologies really could keep up with the price and cost development in the crystalline technology. So therefore, I will focus on crystalline silicon technology, and we'll talk about one idea how to increase the energy output, and this is also an idea which can be used by medium-sized and smaller module manufacturers. So if we talk about different areas in the world, then we have in every area in the world different global irradiations, different ultraviolet conditions, temperature varies, and also we have different rain and humidity conditions. So far, all manufacturers have one module type and they sell that to all parts of the world. I think in the future this will not be the concept, because you have to design modules for certain areas, and for instance in this area here it is not necessary to design a module which can withstand snow loads. I mean, but most of modules bring that with a standard design. So therefore it would be a good idea to design modules as needed for a certain application, use existing cells and just produce the module. If you want to do and if you want to optimize a module, then you have to compare on one side what are the environmental conditions, on the other side what you can do in your module, and what are the parameters which will be influenced. So what we have mainly is, as mentioned, the soiling question, especially in that area. Normally the mechanical loads, especially the external by snow loads, as mentioned, they are not existing, but there are other ones which comes from higher temperatures and also higher temperature change between day and night. And I will show you an example how critical that can be. In some of the areas, even if it is hot, we also have a high humidity. And we have a higher radiation, which is good, but also with the higher radiation comes a higher amount of UV, which leads to some reliability issues, especially for the encapsulation material. On the module side, we have on the front side a glass with an anti-reflecting coating, which can be adapted to the local application. We have a frame structure, as mentioned, that can be reduced. We have the encapsulants and the backsheet, which are very sensitive to UV irradiation, and we have an interconnection in the module, and we also can use specific cells which have advantages for the applications on the left side. So now you can do a lot of analysis if you consider those points, and I just want to highlight a few of them. One is how to increase the output of a module by using standard solar cells and just changing the way how to make the interconnection in the module. And this is a half cell concept which I will show, and this has some advantages because we can use the radiation in a better way, and it also has some benefits for higher temperatures. So what is the motivation again for that is the industry wants to increase this cell to module power ratio. So that means this is it's the power of the module after you have interconnected, for instance, 60 cells, and you divide that by the power of the single cells and the number. And normally you would think, okay, the maximum value which I can reach is 1, but this is not necessarily true. You can see that the goal in the industry is to have an increase or a value which is larger than 1. So that means the power output of the module is larger than the sum of the single modules. So the question is, how can that happen? The general reason for that is if you normally take cells, this is if you just would take 60 cells, you add the single power, you would end up with 285 watts, and if you would build a standard module, the power would be 265, I think in that sample, 55. And there are a couple of losses. So it's optical losses, but there are also optical gains, and there are electrical losses. So the principal idea is if you can get rid of those optical losses, electrical losses, and you can use those optical gains, then you can get CTM values which are larger than 1. So what I'm going to talk today It's not of the optical ones. There's a good publication from our institute, what you can do. I will just talk about that electrical losses, because this is, as mentioned, a way which can be easily integrated. So the way how to do that is very simple from a technical point of view. You take a standard solar cell and you cut the solar cell in 2 pieces. And what you do with that you reduce the current, and by a factor of 2, because you have 2 half cells, and the electrical losses, they scale with the square of the current. So that means if we just have half of that, we have a strong impact of the reduction on the electrical losses. So just to have a very simple analysis of a 60 cell modules, which is the standard in the industry, we have a typical loss just by this resistance loss, the electrical loss in the module, in the copper ribbons of 8 watt. If we use the half cell concept in a module, we can reduce that value to 2 watts. So we have an increase of 6 watts in the module, which would be something a little bit more than 2%. So that was the idea. So the question is how to do that. There are a couple of companies which already trying to bring products to the market. So there's an overview which company has some product development. There is one production which started this year from REC in Singapore. They have a module which is based on this half cell concept, which they called Twin Peak, and I guess also the other companies will follow next year. So what you have to do in order to produce such a module, you buy standard solar cells. You have to cut those cells in 2 parts. There are challenges and technology possibilities how to do that. There are mainly 2 technologies which are currently available. This is a combination of laser scribing and mechanical cleavage. And the new technology which we currently developing together with a company in Germany is a thermal laser separation. And so the simple way is like that. You have an industrial solar cell, you scribe that, then you have a mechanical separation, and then you have 2 cells. As mentioned, there are different ideas and different possibilities. The technology which is used right now in the industry is this one. You have a mechanical scribing from the rear side, then you apply a mechanical load, which is only a small one. Then you break the cell here and you have 2 parts. We have a patent pending, just changing the 2 steps. So apply a mechanical load and then scribe the cell, which is reducing some issues in handling. And as mentioned, this is a technology, the thermal laser separation, where you do not need, or we do not have any thermal ablation. You just need thermomechanical stresses. Okay, we have developed with the CERES, which is an institute in Singapore, together a technology which has a specific wiring approach. This is based on a 72 cell module. So this is a module type which is used for large PV power plant installations. And so we have 144 half cells. And we changed a little bit the wiring compared to a standard one. And the idea was, with that system, we can use a standard junction box with 3 bypass diodes. And the way is just we have strings which are wired in this direction. This one is parallel, and then we have a serial connection. So as mentioned, we have a module line where we even can produce modules in that size. So we did that at the institute. You see that the cells after the cutting, after the wiring, that's the cells before the lamination. And then we get the full module, and then after that we can compare the properties of the full module, or the module with the full cells with the half cells. And what you see is that we got an increase of nearly 5%. So with the half cells, with the same cells, just wired in a different way, the power output under standard conditions, which means 1000 watt per square meter, and ambient temperature was nearly 5% higher. And you see, a part of that is contributed to the electrical improvement, but the other one is also some optical gains, because we can use more of the light which comes into the cell and is into the module and is reflected from the rear side of the module. So So that means it was even more than we predicted or guessed before we started with that development. So then we started to install those modules in a test field in Germany. They are now installed for the first development we started in 2013. They are in a fixed installation and the modules are measured every 10 seconds. And just to make it a little bit clear, what you see here is the difference between the energy production between the half cell and the full cell module. And you see that in the summer months or even in spring, that the monthly energy output for the half cell modules is 4% higher compared to the full cell. In winter, it's much lower. The reason for that is, if you go back to the basic idea, that we reduce the current, and current scales with the resistive losses scale with the square of the current. In the winter months in Germany, we have a lower irradiation, so that means this effect is not so present in the winter months, but in summer months or in areas where you have a permanently high irradiation, you have that improvement the entire year. So even in Germany, the average per year is you have an increase of 3% with that. And people quite often say, okay, just 3%, you know, it's nothing. But if you think about going back to the initial calculation, I mean, 3%, it depends on your interest rate, which you have, that can be decide if your project is competitive or not. So with the analysis which we have and data mining which we applied, we can calculate the improvement with that type of modules for different irradiance conditions and also different ambient temperatures. And you see at days with a high ambient temperature in Germany and high irradiance, we get high improvement. And another thing which we observed, that in the field, the improvement was higher than we measured under laboratory conditions. If you remember, that was the value of 4.7%. We could see in some days that the half cell modules have an increase of 6%, and that's especially in that conditions which you have in areas with high radiation and high temperature. So what's the reason that we get that additional benefit? So what we found is that those half cell modules, they're always colder than the full cell modules. So you might wonder what's the reason for that. I will show that on the next slide. But if a module can stay at a lower temperature in an application because of the temperature coefficient of a solar cell, this has a strong influence on the power output of a module. So just by increasing the average temperature of the module, which we observed in the field of 3 degrees Celsius, we can increase again the power output by 1.3%. And the reason for that is, this is a thermographic or dark look-in thermographic measurement. The left picture is a full cell module and the right one is this half cell. And you see that especially in the interconnections, the ribbons, which are these areas here, these modules stay colder. Again, it's clear if you think about the basic physics. We reduce the resistive losses in the interconnections, and we do not produce electric heat, we produce electric energy, and therefore we get higher electric energy, but we also reduce the temperature, which has a strong effect on the power output. So with that, we just a summary at that position. So do I have to fast up? So I have a second part on reliability, and I have to go very fast to that. Because in the program was a time of 45 minutes. I just talk. Okay, and I have 10 minutes to talk, but I can speed up as mentioned. So, in our opinion, there's a technology which can be used and has a great potential for desert application. And also the advantage is for module manufacturers in that area. You can buy cells from international companies and you can establish a technology based on that idea here in that area. Okay, some reliability issues. Just a summary, what we have seen over the last 8 years in analysis of failures in modules. So we do a lot of reliability studies for a lot of PV companies and also investors. There are different types, different reasons why modules can fail. I just want to talk about two things: the potential induced degradation and fatigue of copper. Potential induced degradation is something which was observed in the field a few years ago, was not observed in the laboratory. So this is something which you have to consider if you install modules. And what you see in that map is this is an analysis from an institute in Berlin that is quite often occurs in very warm regions and regions which are very close to the sea. And an example is that is where we were involved, that are modules from installation in Italy. So after 10 months, the degradation was nearly 50% of the modules. So actually, this was a survey which we performed last year, where we tested 100 commercial modules which you can buy, and all those companies will tell you my module is PID resistant. But if you do a laboratory test, then you see roughly 50% of the modules failed, so they are not PID resistant, even if the companies tell that. You can investigate that in the detail. I will skip that slide, which is explaining what's going on the cell level. What we have developed and licensed to a company is a test procedure to test that PID resistant on a cell level. Before that, it was necessary to build the entire module and then do module test, which takes a week, production of module and testing. With that, within hours, you get an information if the cell is resistant or not. And okay, this company also already started to sell that, and more than 30 of those machines were sold this year. And it is used by cell manufacturers to control the quality, but you also can use it as a module manufacturer because you can check the quality of the incoming cells. As mentioned, if you interconnect cells, you have mechanical parts, and if you have a temperature change between day and night, those interconnections might fail. You see that in an electroluminescence image. This is an optical image, and if the interconnection fails because you have current flowing through that area, there's a chance of spark formation and high temperatures, which can really lead to a severe damage of the module. And actually what's going on is you have a temperature change between day and night, and in a desert environment, you see the red curve, you have more days with a higher temperature change. This leads to mechanical stress of those interconnections. You can calculate how big the gap is, and it mentioned in the end, this is the cross-section to a failure of the interconnections. So we have developed a test approach where we can measure the single ribbons, so we can evaluate different vendors, different materials. Secondly, we have developed an approach where we can look into the module while you change the temperature conditions, and you can measure the change of the gap between the cells. And secondly, you have to understand the mechanical properties of the polymer in detail. There's also an approach which we have developed. And if you take all those three informations, you can, using finite element simulations, to predict what's going on. For that, we have a full model of our a crystalline silicon module. Then we can apply external load. We consider the internal situation, the cell, the materials, the encapsulation, the wiring, and then we perform different temperature changes, and we can calculate, in this case, the plastic strain which is occurring in those interfaces. So with that, you can analyze if my module will fail or not, because you know how many temperature cycles will occur, because you have the weather data through your installation. With that approach, you can predict in which area here you will be. You can compare that with your measure data. You see if you're on a safe side or on the risky side. Just mentioned, there is a standard which every manufacturer has to fulfill before you can sell a module, this IEC test for temperature cycle, but this just specifies the test in this area. So if a module passes a temperature cycle test, this will give you no information if the module will survive in such an environment like this. So last topic, and that's very briefly, it's dust, and it's a couple of examples where we are involved. This is in Saudi Arabia, this is in Qatar, and this is the test field in Ben Guerir here in Morocco, and you see how severe dust can be on the modules. There's a very nice study from Ben Figgis from the Kerry in Qatar, which he just showed months ago at the conference in Halle. And you can see that if it's not raining and you do not clean, which they did in the test approach, that the efficiency can go down by 70%. So, or on other days, nearly 0.5% per day. There are some other investigations in Saudi Arabia which came up with a little bit lower values of degradation, but nevertheless, this is a main issue. So, the question is, what can you do with that, or what can you do against the dust? One easy thing is to clean the module. There were a couple of calculations. I mean, if you consider certain costs for the cleaning, and the cleaning means we have to get rid of those small dust particles, then this can really contribute additional cost, which you have to consider in your analysis. And it depends. For a 2 megawatt park, it was considered 50,000 euros a year. If you're going back to 1 megawatt, it means at the end, the cleaning costs in the period of 25 years, they are higher than the cost of the module itself. So, I mean, cleaning is possible, but it is, or might be a costly solution. There are right now some development of anti-sticking coatings, or some systems with electrostatic charging of the surface. None of technologies have a long-term experience, it's not proven. And again, this is some from Ben, which he showed a month ago, and they tested different coatings, and none of these coatings really showed an improvement, which you can see here in this diagram. So, short summary of the reliability issue. I mean, we have a lot of experience and also currently trying to bring that in R&D projects together with partners in different countries, like in Morocco and also in Qatar. Some of the really failure mechanisms which you have to understand and which you have to consider in the layout of a PV power plant is potential induced degradation, and you have to consider that your interconnections will not fail because of the temperature changes which occur during day at night. And the last point, so soiling, dust, it is something which is currently unsolved, and there are some solutions needed in the future to bring PV systems also to those areas in the world. So with that, I would like to thank you for your attention, and I'm open for any questions.